Hey guys, it's Mr. Post, and on today's video we'll be learning how to write Lewis dot structures for covalent compounds. And we're going to start off by illustrating the necessary steps you will be taking to write your Lewis dot structures. The first step in writing a Lewis dot structure for a covalent compound is going to be to count the total number of valence electrons specifically. So if you check out this picture here, we have H2O. That's the molecule we're looking at, and these are steps for covalent compounds only. So what we're dealing with right here is a hydrogen, which has one valence shell electron, another hydrogen, which still has one valence electron, and an oxygen. And that oxygen has 1, 2, 3, 4, 5, 6 valence shell electrons. So really we're looking at 1, 2, plus 6. We're going to have 8 valence electrons we're dealing with. The second step is going to be to write the skeleton structure for the molecule. And we're going to remember to put the element that needs the most electrons in the middle of our skeleton structure. So our skeleton structure is going to be kind of like a basic, bare bones Lewis dot structure. So the element that needs the most in order to get to an octet is going to be oxygen. So if we check this out here, guys, oxygen has 6 electrons in its outer shell. It needs 2 more. Hydrogen actually only needs 1 more. It's not going to form an octet. It forms what's called a duet. And my skeleton structure that I'm looking at you drawing is something like this, where I have my H2O down, the element that needs the most electron goes in the middle. Think about it this way. I'm going to draw hydrogen on the outside here. Hydrogen has 1 electron in its outer shell. Really, all it can do is reach inward towards the molecule. It can never form a bridge. It can never be a central or middle element. Same way, if we take fluorine or any other element in group 7, they can only form 1 bond and kind of reach in towards the center. They cannot form a bridge because they have 7 already. When I'm saying form a bridge, I'm talking about like the element oxygen. Oxygen has 6 electrons in itself, so therefore it can actually link this way and that way. Another great element to do that would be nitrogen, because nitrogen has 5 electrons in the outer shell. It can form a great bridge because it can bridge in 3 different directions. And the best of all, we're going to have carbon. Carbon or silicon, they bridge and form awesome central atoms because they bond in so many directions. So the step number 1 was to count the total electrons up. We got that at 8. Step number 2, write the skeleton structure and put the element that needs the most electrons in the middle. That's what we got here, guys. Step number 3 is going to be to use 2 valence electrons to form each bond in our skeleton structure. So I'm going to redraw my skeleton structure right now. There I have my H's and my O's. And check this out. I'm going to use 2 valence electrons. 2 of my 8 that I have to place. 1, 2. That represents a covalent bond. And I'm going to draw that over here as well. So I'm using now 2 valence electrons to form each bond in the skeleton structure. These are bonds. So what we have here, guys, is one H2O molecule. And within the H2O molecule, I have 2 covalent bonds. I started off with 8 electrons. Dudes, I just placed 4 of those electrons, meaning I actually have only 4 electrons remaining. That's right, there's 4 left to place now. So this is what I got now, dudes. I have my 2 electrons here, 2 electrons there. I had 8, used 4, I'm down to 4 left. Last thing, step 4, you're going to make octets. That's right. The whole goal here is to have 8 electrons in our outer shell. And we're going to make that by distributing the remaining 4 valence electrons. And we're going to do so in pairs. So I'm going to place 1, 2 right here. And 1, 2 right there. And guess what? Dudes, I'm done. I'm out of my electrons. The question now is, do I have octets? Step 4 said to make octets. That's my goal. I'm not done with the step unless I've made octets. Well, let's check this out. 2, 4, 6, 8 electrons around oxygen. That's right, I got my octet. Hydrogen does not need 8, it only needs 2. And guess what? It's going to count these 2 right there as its own. These two are its own as well. So I got my duet there, and I got my duet there. One cool thing with covalent bonds, you notice I counted those electrons right there for oxygen, and these electrons for oxygen as well. And when you share electrons, both parties, both H and the O, have ownership over the shared pair, and they're counted twice. Alright, dudes, let's get going on another problem here. What we've just formed is two single bonds. A single bond is a single pair of electrons that are shared. This is a single pair of electrons. That's a single pair of electrons. And I have made two single bonds within my covalent molecule of water. You can also express the covalent bonds as lines or dashes. It's a very common thing to do. Instead of using dots, represent it as a dash. Really, it represents a dot there and a dot there, an electron there and an electron there. So we as scientists want to make it a little faster, a little neater actually, and sometimes it's really clean and easy just to draw a line instead of two dots. Alright dudes, you know the drill. You've seen the steps. I want you on your own to try drawing the Lewis dot structure for nitrogen tribromide. Give it a shot, dudes. Alright guys, what we got here? We got to count up the total number of electrons. Nitrogen has 5 in its valence shell. Bromine has 7 in its valence shell. Now let's multiply that by the number of elements or atoms you have of that. We have 5 times 1 nitrogen gives me 5 electrons contributed by nitrogen. Dudes, I got 3 bromines. That's NBr3 times 7. That gives me 21 electrons to space out. All together, I'm going to add them up. I have 26 electrons I'm responsible for placing. That was step number 1. Step number 2, let's throw down our skeleton structure with no bonds yet. No bonds. We need to determine which one goes in the middle. Well, if bromine has 7, it only needs 1 more. Not a good middle element. Nitrogen, on the other hand, makes an awesome middle element because it needs 3 more electrons. So we're going to throw nitrogen in the middle, and we're going to put bromines around it. And if you recall from before, bromine can only reach in with 1 arm, kind of. So it is not going to form a chain. You can't link it up to anything else. You can only form 1 bond. So let's do this up, dudes. We got step number 1 down. Check. Step number 2, I got right over here. Check. Step number 3, distribute my 2 electrons to form covalent bonds. There we go. I've made 3 covalent bonds. All 3 of these are single bonds. Now I've used 6 electrons. I'm down to 20 left to place, and step 4 said place these in order to make octets, and you're going to place them in pairs, meaning this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And I've used up all my valence shell electrons. Now the question is, do I have octets? 2, 4, 6, 8. 2, 4, 6, 8 on bromine. 2, 4, 6, 8 on nitrogen. And 2, 4, 6, 8 on bromine. That's right, guys. I have myself octets everywhere. Cha-ching! We got that one done. Alright, dudes. Let's try the same thing for oxygen. The same 4 rules apply. Make sure you follow it step by step and give me the Lewis dot structure for oxygen. I want you to take a shot at this yourself and then come back and see if you can actually get the problem right by checking your answers versus mine. Do it up, dudes. Step 1 says to count up the total number of valence electrons. Each oxygen has 6 electrons in its outer shell, and I have 2 of those, so I'm going to make 6 electrons in my outer shell times the 2 oxygens I have in O2 is going to give me 12 electrons to place in my Lewis dot structure. I am committed to placing 12, no more, no less, in order to achieve octets. Step number 2, draw the simple skeleton structure. Simple skeleton structure just shows the elements, nothing more. Now, a real skeleton structure, though, is going to include the bonds. We're going to place step number 3, a bond between them. Now they're linked together by a chemical bond named covalent bond. It's the sharing of electrons. Dudes, I don't have 12 electrons anymore. Now I have 10 electrons to place. Now, step 4, place them around and don't stop until you get octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Check this out, guys. I'm out of electrons, but I don't have an octet. You check this thing out here? You see it? I have 8 electrons right there, but on this element, this oxygen, I have 2, 4, 6. That is not an octet, and I have no more electrons to place. The really cool thing with covalent bonds is that literally I want you to do this. You take a pair from the one that already has 8, and we're going to move that pair into the middle here to be shared again. So I'm going to scratch off these guys here, and now move them right down there. That's awesome. Check that out. So this oxygen over here still has 2, 4, 6, 8. Now this one, though, on the right-hand side has 2, 4, 6, 8. So I don't have 6 electrons anymore. I have 8 electrons. That's right. What it's looking like, guys, is this. I have what's known as a double bond. And I'm also going to draw the remaining electrons, and I'm going to space them apart. And so my Lewis dot structure for oxygen actually shows one double bond shared in between the 2 oxygens. And a double bond really is another way of saying there's 4 electrons that are shared inside there. What's a double bond? Specifically, when 2 pairs of electrons are shared between the elements, we represent them as dots for electrons. We can also represent them as lines, as I showed before. Alright, dudes, next one, nitrogen. Anytime we have 2 of one element, we're going to use the element's name, which is nitrogen. How many valence electrons does this have? Go ahead, guys, launch us through, solve the whole problem, come back and see if you got it right. Each nitrogen contributes 5 electrons to the molecule. I have 2 of them, so really it's like 2 times the 5 electrons they contribute gives me 10 electrons to place in my Lewis dot structure. No more, no less. So let's write down what we have here. The simple skeleton structure looks like this. I'm going to drop a pair of electrons right there. I had 10. I'm now down to 8. Awesome. Let's place it 1, 2, 3, 4, 5, 6, 7, 8. Gosh, we got 6 electrons in this element, the 2, the 4, the 6. We got 2, 4, 6 over here. Not looking too good for us. Well, let's start sharing more than one pair in the middle. Let's take this pair on top here, remove it, and place it in the middle. Boom. We did so. What do we got now, dudes? The one on the right has 2, 4, 6, and 8. Awesome. It's got the 8 electrons. The one on the left, though, has 2, 4, 6. So you're going to take 2 now from the one that already has 8. You're going to take an extra pair. Let's just grab this pair here, and we're going to move that into the middle to be shared again. Now this is gone. What do we have? We got awesomeness, actually. This is awesome. We have 2, 4, 6, and 8 on the right-hand one. So we have 8 electrons right here. That's an octet. On the left side, 2, 4, 6, 8. We got an octet, dude. So when we write this over nice and neat, we have a triple bond between the 2 nitrogens, and now we still have to address these extra pair of electrons. We're going to put them and spread them apart away from the middle, so it's kind of 180 degrees away. My Lewis dot structure for N2, which is nitrogen, looks like this. A triple bond is when 3 pairs of electrons are shared between the elements. In this case, this one molecule has one set of triple bonds. Alright guys, rock it out. Try out the Lewis dot structure for carbon dioxide. Carbon is going to bring 4 electrons to the table. It has 4 electrons in its valence shell. Oxygen, and I have 2 of them, each one is going to bring 6 electrons to the outer shell, and I'll have 2 times 6 for 12 electrons. Let's add up 4 plus 12. We're going to have 16 total electrons to place in my Lewis dot structure. The element that needs the most electrons goes in the middle. Well, carbon needs 4 more electrons to get to 8. Oxygen only needs 2. So therefore, carbon becomes the central atom. And I'm going to place my oxygens on both sides of it. The next step is out of my 16 electrons to place bonds between the 2, represented by a pair of electrons. So I've placed 4 electrons, dudes. I'm down to 12. Your job now is to distribute the remaining 12. Let's do so kind of in an equal fashion. 2, 4, 6, 8, 10, and 12. We're done. We're done throwing this down, but you're not done yet. You still got some more work to do, guys. We have 8 electrons over here, 8 electrons over here, but we only got 4 electrons right here. And step 4 says make octets, and we haven't made the octets yet. We're going to have to do some more sharing here. We're going to take 2 electrons from one that already has like 8. It already has plenty, so we're going to take that, put it right there. These electrons are now erased. They're not there anymore. This oxygen still has 2, 4, 6, and 8. Carbon actually has 2, 4, 6. So it went from 4 to now 6 electrons, but it's not at the octet yet. So let's go to this side now. On the right-hand oxygen, let's take one of these pairs of electrons. Let's just take this one down here. We're going to move it from right down here. We're going to go right there. And it's going to be now shared again. So what we got here is carbon now has 2, 4, 6, and 8. We have the 8 electrons it desires to make the octet. I hope you see what's going on here. I have a double bond here and a double bond here. I should say a double bond here, a double bond there. What we have here is one double bond over here and one double bond over here. That's what I meant to say. And I want to draw this kind of a little bit nicer now. Carbon's in the middle. We have an oxygen over there, double bonded, and a double bond going in that direction too. I have my extra pair of electrons. They're called unshared. These are my unshared pair of electrons. And this is the Lewis dot structure for carbon dioxide. It's pretty sweet looking. Next up, guys, is a pretty challenging one actually. It's carbon monoxide. For one oxygen, monoxide. Take it away, guys. Carbon is going to bring 4 electrons to the table. I have one set of carbons, so therefore I have 4 electrons donated from carbon. Oxygen, though, has 6, but I only have one of those, and so therefore I'll have 6 electrons brought to the table by it, for a total of 10 electrons to place in my Lewis dot structure. No more, no less. We cannot create electrons. Next thing, let's write our kind of skeleton structure down there, and we're going to throw our bond in the middle. Now we're down to 8 electrons. Let's place them, dudes. 1, 2, 3, 4, 5, 6. Where else do we want to place this? Well, let's just place it right here. 7, 8. Clearly, we have one element that has 8 electrons and one element that has 4. And it really doesn't matter how you actually put these electrons down. They're all going to work out in the end. So let's do this. Oxygen is going to donate that pair right here. So that pair is gone. Oxygen still has 2, 4, 6, and 8. Carbon now has 2, 4, 6. That's an improvement, but we don't have 8 yet, dudes. What are we going to do? Well, if you take these and put them in the middle, carbon would still only have 6. So therefore, oxygen is going to have to donate another pair. It's going to take those guys and drop them right in the middle too. Now these guys are gone. That's actually called a coordinate covalent compound, where oxygen is actually donating more than one pair of electrons to the bond. And when I redraw this nicely, what you're going to see, I have a triple bond between carbon and oxygen. I have the extra pair of electrons placed over here, and an oxygen, it still has that extra pair of electrons right there. This is the Lewis dot structure for carbon monoxide. Good job, guys. And the last Lewis dot structure we're going to examine today is going to be ozone, which is O3. Each oxygen is contributing 6 electrons. Therefore, I have 3 of them, and I'll have 18 electrons to place in my Lewis dot structure. No more, no less. It's going to be pretty obvious that oxygen has to be in the middle in this case because it's all oxygen. We're going to bond them up and link them with single covalent bonds to start off with. I've used 4 electrons. I'm now down to 14 electrons. You place the remaining ones anywhere you want. I'm just going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Awesomeness, because we have 8 here, we have 8 electrons here, and 6 electrons there. Check this out, my battery's running out. Oh man. Let's try and make it through this video here though. So what I have now is I have a needy element on the right hand side, and because it needs, it's going to get it's going to borrow the electrons or share them with the one that has an abundance. The one that has 8 will take one of the sets of electrons. Let's just grab that one and put it in the middle. I now scratch that off, and guess what I got, dudes? 2, 4, 6, and 8. That's 8 electrons on this one. No longer has 6. This one still has 2, 4, 6, and 8. It's got 8, and this one has 8. And my Lewis dot structure ends up having a double bond over to the one side, a single bond over to that side, and I'm going to have my extra electrons all around. This is a really cool Lewis dot structure. It is not necessarily the correct shape. It's not going to be a linear shape per se, but the Lewis dot structure looks awesome. You could also write this Lewis dot structure a different way. And that would be having this oxygen on this side, having the double bond going to that, and that going over there. And I would have to write in the remaining valence electrons as well, such as those dudes, these dudes, and then those guys there too. Alright guys, thanks a lot for tuning in today. We're looking at Lewis dot structures, and I hope this video was helpful in you learning that topic. Alright guys, peace.